In this video, I will take you line by line through the free FreeRTOS Arduino demo sketch for ESP32. Let's start by opening the Arduino Integrated Development Environment. Now we are going to open the free FreeRTOS sketch for ESP32. Sketches in Arduino are the source files for your program. Click on File, Examples, navigate down to ESP32, and click on FreeRTOS. This sketch of a basic FreeRTOS program is included with the board support libraries for the ESP32. To install the Arduino IDE and these libraries, please take a look at my video, Setting Up Arduino for the ESP32. Let's dive into the source code. The first line begins with a hashtag. Any line that has a leading hashtag in Arduino, as in any C or C++ programming, is a precompiler or preprocessor directive. A preprocessor directive is code that is not going to be processed while your program is running. Instead, the precompiler will do some work with the directive before the source file is ever turned into machine code. This allows for more advanced configurations, the inclusion of libraries or other source files, reduces actual program overhead, and makes the code more reusable. Since we are on the topic of preprocessing, this is a great time to talk about the Arduino toolchain and how preprocessing or precompilation fits into the build process. The topic of preprocessing is too vast to make a definitive guide part of this video, so I am only going to cover some important basics. When you issue the compile and test command or the compile and upload command, the build chain starts doing the work of converting your source code or sketch into machine code. The first step is what is called a syntactic check. In this check, the toolchain reads through your code to ensure that you did not misspell any commands or forget a semicolon on the end of a line. You can think of this step as the source code grammar police. It is going to argue with you until your source code fits the common rules and standards of C and C++. It does not check for coding mistakes or read your comments. It checks only that the actual code follows all of the basic rules of C and C++. Once the syntactic check passes, the actual precompiler takes over. This part of the build chain substitutes header files for includes, as well as values from directives into the text file. You can imagine it doing the work you would otherwise have to perform of copying and pasting pages of pre-written code needed to complete the program. Once the precompiler finishes, the completed text is loaded by the actual compiler, which creates an assembly language file. The compiler automatically includes all the machine instructions specific to the processor being compiled for. Now the assembly file is handed to the assembler, which builds machine code. The machine code is then passed to the linker, where any pre-assembled binary includes are linked with it. At this point, the file is a completed executable, and the uploader sends it to the board. Back to the FreeRTOS sketch. The first precompiler directive is the conditional logic expression if. If examines a condition, and if that condition is true, the result is true or affirmative. The condition being tested is if config FreeRTOS unicore was set by the build files. Unicore is FreeRTOS configured to run on only one core. Each core on a microcontroller can be thought of as an independent processor. A single core can execute one thread or task at a time. The else statement in our sketch is a conditional statement which evaluates true only if the preceding conditional if statement evaluates false. In this instance, Arduino running core will be set to equal 1 if config FreeRTOS unicore is not set. This section could have multiple definitions, as the preprocessor or precompiler will process all statements until the end if statement. Next, we have another set of preprocessor logic and a definition. This time, the logical expression is if in def, which stands for if not defined. This section could have multiple definitions, as the preprocessor or precompiler will process all statements until the end if statement. If the test if in def LED built-in returns true. The default definition used in this sketch for the built-in LED points to pin 13. On most Arduino boards, pin 13 is the integrated LED. On my Node MCU32S development board, the built-in LED is actually on pin number 2. The hashtag endif statement tells the precompiler the if-in-def code block has ended. In the sketch, we now encounter our first code comment. Line comments use the leading double forward slash to tell the compiler to ignore them. Any text following the double forward slash on the same line is ignored by the toolchain. Comments are useful if you have to rework your code and remember why you did something or what a particular piece of code does. Comments are also useful when more than one person is working on a piece of code or the code is distributed to other users. This comment tells us the following lines define two tasks, blink and analog read. This is not entirely correct, as the following code is of declarations of functions, not definitions. When we create a function in C, first we declare the basic outline for the compiler to recognize it when it sees the function called throughout the rest of the program. In the declaration, we only outline what type of data the function will send and receive, as well as the function's name. On to the actual task declarations. These are the same as any function declaration in Arduino, except they must always take a pointer to PV parameters. They return nothing. Pointers are beyond the scope of this video, but to oversimplify, a pointer is a variable that does not hold data but instead holds the address to a piece of data. You can recognize a pointer in this format because it is a variable preceded by an asterisk. When you declare a function or task, you must define both the input and output data types of the function. The input goes into the right, and the output is what is returned by the function when it ends. This is on the left. A declaration is formed as return type, function or task name, then arguments within parentheses. All lines in C and C++ need to be ended by the semicolon. After the task declarations, we come to another comment telling us the setup function runs once when you press the reset switch or power on the board. The setup function is where we put things that only need to run once. Traditionally, things like the configuration of pins for output or input are placed here, but that assumes the majority of the application runs in the loop function where everything is repeated. Some things are still configured here, but a lot of the pre-configuration can be moved to tasks outside their individual loops. With FreeRTOS, setup is where task scheduling is configured. Notice the definition states setup returns void and takes no arguments. This is because it is defined as the entry point of our actual program. There are no calling functions to pass arguments in or return data to. We can tell this is a definition and not a simple declaration of a function because it does not end with a semicolon. Instead, the first line of the setup function ends with an opening brace. The opening brace means the nuts and bolts for setup will be found between this and the closing brace. The code block of a function always begins with an opening brace and ends with a closing brace. The next comment explains the next line will initialize serial communication and set the baud rate. The call serial begin is the first C++ object call we have encountered. This is actually calling the function begin that belongs to the class serial. We pass the function begin the baud rate. This sets up the serial port to prepare it for communication at our desired baud rate. We then encounter another comment that tells us the following code sets up two tasks to run independently. Now we have reached the actual code for task creation in FreeRTOS. The function called is xtaskCreatePinDecor. It takes the following arguments separated by commas. The machine task name. This is the name of the actual function or task that was declared earlier in the sketch. Next is the human readable name of the task. This is not actually used by the task scheduling, but is stored for human identification of the task. This way, the task can be easily identified if you are examining the memory stack. Next is the stack size for the task. Stack size can be difficult to calculate as it changes according to how many functions are called by the task. nesting depth, number and size of scope variables, the number of function parameters, processor architecture, and compiler options. Setting the stack size too large wastes resources by locking memory out from other uses. Setting the stack too small can cause a stack overflow. A stack overflow is when data written to the stack exceeds the space dedicated to the data, and values are written over onto nearby memory, which may or may not contain other data. If these regions of overflow contain no data, there will be no indication this is occurring. But if this overflow region of memory contains important data, it will be overwritten and corrupted. Thankfully, there is a utility built into FreeRTOS which can report the maximum used stack size which occurred during execution. This handy utility API is UX_task_getStack_high_watermark. This utility reports the amount of stack not used. This is reported in words, so the meaning of the returned value changes depending on the architecture of the microcontroller being used. A word is a data type whose size is determined by the architecture of the microcontroller. With the ESP32, the word size is 32 bits, as the ESP32 is a 32-bit microcontroller. The next parameter within task creation code is PV parameters. To simplify things, this is set to null. PV parameters is used by the FreeRTOS task scheduler. Next is the priority level of the task. This runs from 0 lowest to the max set in configuration -1 as the highest. As an example, if the max priority is 2, the options are 1 and 0, with 1 being highest priority and 0 being lowest priority. The next argument is px created task. This is a handle to the created task and can be null. The final argument is a reference to the core where the task is to be run. If you remember from earlier, we know that the value is 0 if the configuration is for unicore. Otherwise, it will be 1. The closing parenthesis tells us we've reached the end of the arguments to the first xTaskCreatePin-to-core function. Now we come to the scheduler code to create the second task in our demo. This is mostly a repeat of the last block of code, with minor differences because it creates a different task. After this block of code, we find another comment explaining that the task scheduler automatically starts when setup finishes. With other builds of FreeRTOS, you actually have to start the scheduler. The next section of the code is the loop function. With a traditional program in Arduino, this is where all the work happens. After the empty loop function, we encounter a new type of comment, the block comment. The /* indicates the beginning of a block comment, while the */ indicates the end of a block comment. Anything on either side of the comment can be executed, and such a comment can cover multiple lines. This comment tells us that the definitions for our tasks are coming up. Now we have reached the definitions for the tasks. These definitions are the actual code that defines what the task does. These task definitions are identical to any function definition, with the exception they have to take the argument a pointer to PV parameters. The first task we see is task blink. The first line is a call to create the task dataset, PV parameters. Now we encounter a block comment that explains the purpose of the task. Good comments really make it a lot easier to dissect code and actually make sense of it. Speaking of comments, if you have any questions or requests for something you would like to see covered in my videos, leave a comment and let me know. Next, we see the Arduino function pin mode. Pin mode is used to configure a pin on the microcontroller as input or output. An input pin reads changes to voltage applied from an external source to the pin. Setting the pin to be output allows its state to be set from inside the microcontroller. Once set to output, a digital pin can be set to on, voltage applied, known as high, or off, connected to ground, also known as low. In this case, the pin is being set up as an output because it will be used to turn an LED on and off from inside the program. Pin mode takes the pin number and the use as arguments. LED built in was predefined at the beginning of the program as 13 because most Arduino boards have a built-in LED on pin 13. Now we enter an endless for loop. The normal format of a for loop is for, initialization, condition, and increment. The initialization value is what the for counter is set to when it begins. The condition is the state that allows the for loop to run if it evaluates as true. Finally, we have the increment command. This is to change the value of the variable evaluated by the for loop. An example of this sort of loop would be as follows. In this example, the for loop contains an int variable with an initial value of 0. The condition for the loop to run is x equals 0. The double equals sign is used to denote an equality test. Then the variable is incremented with the plus plus operation. Plus plus means the variable equals the variable plus 1. In this situation, the loop would run once. The variable x would become unequal to 0 and the loop would exit. If a for loop has no inputs for initialization, condition, and increment, it will run indefinitely, as is the case with this example sketch. There are other ways to utilize for loops, but they are beyond the scope of this video. Because there are no parameters in the for loop in this example sketch, the loop will never end. This mechanism in a task replaces the loop function of a traditional Arduino program. The first function call inside the for loop is the digital write function. This function is built into Arduino. It takes the arguments pin and state. Earlier we saw the definition of LED built in is 13, so we know the precompiler will replace LED built in with 13. There is then a comma, and the second parameter is passed in. In this case, the value passed in is high. What this does is connect the target pin to the power bus inside the processor. The pin will now have voltage present. If the pin mode would have been set to input instead of output, the pin would now have the internal pull-up resistor enabled. The next function, vTaskDelay, is part of the FreeRTOS library. This function is the FreeRTOS replacement for the integrated Arduino delay. It takes time in the form of milliseconds for a delay argument. The Arduino version delay stops all program execution for a given time. The FreeRTOS vTaskDelay instead blocks the task for a given amount of time and allows other tasks to continue running so the processor is not wasting time idling. The end result is the same time delay of thread execution, but with FreeRTOS, other work can be performed during this downtime. This is a key feature of FreeRTOS, the ability to quickly and easily block task execution while allowing other tasks to continue. This delay controls how long the LED is turned on before the next line executes. After the delay, the next line of code is digital write again. This time it is setting the pin low, which puts the pin to ground. This, combined with alternately setting the pin high, has the effect of flipping a switch from on to off connected to the LED. Then we have another call to vTaskDelay to delay the thread. The delay time here changes how long the LED is turned off. This brings us to the end of the function or task's for loop. The loop now repeats itself from the beginning. This means we return to the digital write call and set the pin high once more. If this pin is attached to an LED with a resistor and the other end of the circuit is connected to ground and the polarity of the LED is correct, it will blink as the pin is switched on and off. After the never-ending for loop, we find the end of the task. Next, we come to the task definition for task analog read A3. Again, we see the line void PV parameters. Then we come to the endless for loop for this task. Inside the for loop, we see our first basic variable. This variable is of type integer, which is specified by the leading keyword int. The name of the variable is then set as sensor value A3. This can be almost any name as long as it does not conflict with any other namespace. You will notice it adheres to the camel case convention of naming. This is the de facto standard of programming style in Arduino. With camel case, the first word begins with a lowercase letter, and each successive word begins with uppercase. This is not necessary to make programs for Arduino, but it makes the Arduino experience more consistent. As long as every time you use a variable name, it is typed the same, style will not impact performance. After the name, the value of the variable is set with the equal command. The equal command in C is not a test of equality, but is used to set a variable equal to something else. In this case, we are setting it equal to the return value of the function analog read. The function analog read reads the specified ADC pin and returns the resulting integer. An ADC is an analog to digital converter. It converts an analog value to a digital value. An analog value is something that is not digital in origin, such as the output from a potentiometer that can have an infinite set of values between two positions as it is turned. The range of an ADC is limited by its number of bits. With an ESP32, the range is from 0 to 4095. This is because the integrated ADCs are 12-bit. 12 bits can be set from a range of 12 zeros to 12 ones. The binary values of 12 bits are as follows from least significant bit: 1, 2, 4, 8, 16, 32, 64, 128, 256, 512, 1024, and 2048. When all bits are 1, the total value is 4095. Now that we have the analog read value stored in sensor value A3, we pass this value to the serial.println function. Println is a member function of the serial object. Println outputs data to the serial port at the baud rate we defined in the setup portion of our program. Println prints the data and adds a new line command to the end of it. This makes the output more legible and easier to parse. After we send the data to the serial port, we delay the function for 10 milliseconds with vtask delay, the same delay function we used in the blink task. After the delay, this function repeats because it is inside an endless for loop the same as the blink task. I hope this video has helped you start understanding how FreeRTOS applies to Arduino and ESP32. If you are just getting started programming, I recommend the Arduino Starter Kit. Working through those projects will help you build a solid understanding of the basics of programming, electronics, and Arduino. If you enjoyed this video, please like and subscribe.